Good morning. This is the fourth class on our fourth unit, magnetic properties of solids. Today we will discuss about a small session, that is neutron magnetic scattering. Okay. An X-ray photon will see the spatial distribution of electronic charge, that is distribution of electrons, whether the charge density is magnetized or unmagnetized. That is, whether the space occupied by the electrons in a material is magnetized or unmagnetized. An X-ray photon can interact with that space. That is what the meaning of the sentence is. A neutron will see it in two aspects of a crystal. That is, one will be the distribution of nuclei and the other will be the distribution of electronic magnetization. Now the figure given below shows just an example for a neutron diffraction pattern. No need of remembering this figure, just I present it for you just for your understanding. Then what happens when a neutron interacts with a crystal? The magnetic moment of neutron will interact with the magnetic moment of the electron. Magnetic moment of the neutron interacts with the magnetic moment of the electron. The cross section for neutron electron interaction is of the same order as that of neutron nuclear interaction. Diffraction of neutrons by a magnetic crystal will help us to determine the distribution, direction and order of magnetic moments. So here this paragraph speaks about the significance of neutron magnetic scattering. That is, it helps neutron magnetic scattering means what happens when a neutron interacts with a crystal. When a neutron interacts with a crystal, it is the magnetic moment of the neutron that interacts with the magnetic moment of the electron. As a result of this neutron electron interaction, you will get a neutron diffraction pattern like this, and from this pattern you will be able to assess or you will be able to determine the distribution, direction and order of magnetic moments. Okay, that is the simple meaning of this slide. Then magnetic moments associated with particular components of alloys may be investigated by neutron diffraction. That is another use. You know, an alloy is composed of a lot of materials, right? That is called an alloy. It will be a composite of different materials. So if you use neutron diffraction technique, you will be able to predict the magnetic moments associated with each of the components constituting the alloy. For example, the figure here shows an iron cobalt binary alloy. The results that you obtain from that, the material is ferromantic. See the various components you can see in cobalt, how much the ratio of elements, how it is present, like that. Then the magnetic moment on cobalt atom does not appear to be affected by alloying, whereas in the case of iron atom there is a particular effect of alloying, that is the alloying it increased to about 3 mu b as cobalt concentration increases. That is, magnetic moment on cobalt on alloying, magnetic moment on cobalt remains unaffected, whereas magnetic moment on iron increases to about 3 mu b as the cobalt concentration increases. So all this comparative study you can make if you analyze the cobalt and or any alloy spectrum using neutron diffraction technique. Okay. So the magnetizations are shown in the figure given below. Now, how does a neutron interacts with a crystal, or how the mechanism of scattering? The scattering is inelastic. That is, a neutron is inelastically scattered by the magnetic structure with the creation or annihilation of a material called magnon. So when we said that when a neutron interacts with a crystal, it will get scattered. That scattering is inelastic scattering. Okay, and that inelastic scattering of neutron by a crystal or by a magnetic structure will lead to the production or annihilation of a material called magnon. About magnon we have already discussed. Okay. Such events make possible the experimental determination of magnetic spectra. See, neutron, you are creating a new material called magnon. Then this is the last slide. Now here they are explaining the phenomena using wave vector k. That is, suppose that the incident neutron has a wave vector kn, and let the scattering wave vector be kn dash, and suppose that it leads to the creation of a magnon of wave vector k. Then by law of conservation of crystal momentum, kn is equal to kn dash plus k plus g, where g is a reciprocal lattice vector. I think this type of equation also you might have come across while studying solid state physics in degree classes. Okay. Then by conservation of energy, they are giving an expression, that is h cut square by h cut square kn square by 2mn is equal to h cut square kn dash square by 2mn plus h cut omega k. H cut omega k is the energy of the magnon created during the process. Okay. Kn dash k and all we have already defined. It is given here. Then the observed magnon spectra for a particular material, an example they have shown here. No need of drawing this figure. Okay, it is enough that you write up to this. Then from here, this slide you can write, and here this paragraph you can write. For if you want, you can draw this diagram, and this slide also you can write. Okay, that is enough. This is all about neutron magnetic scatter.